All right. We are looking at the second half of chapter 35 notes. What we're looking at today, again, in this video is probably going to be looked at a little bit more in an upcoming video dealing with the math of chapters 34 and 35. I may break it into a couple of sections. I'm not quite sure yet. But 35.5 deals with something we call schematic diagrams. Schematic diagrams are diagrams that show us how electric circuits are set up. And they're set up in such a way that we can see or look at how the electrons would flow in the circuit. And it helps us to analyze problems. It also gives a uniformity to the electrical industry so that when somebody from China looks at a schematic diagram from the United States, or somebody from Russia looks at one from Africa, whatever it happens to be, everybody's on the same page. And so if you need to build a circuit from somebody, they send you the schematic diagram, you know what it looks like because they drew it in a system that makes sense to the whole electrical industry. And so in these schematic diagrams, there's a couple of different symbols that we use. Resistance is kind of this zigzag line. If we have a resistance-free wire, again, no wire is perfectly resistance-free, but they're shown as these solid straight lines. Batteries are represented with a set of short and long parallel lines. One a little bit longer, one a little bit shorter. The longer one is the positive side. The shorter one is the negative side. So here we have our different schematic diagram symbols. Again, here's a battery, longer, shorter, couple of wires going off in both directions. Again, this would be the negative side. This would be the positive side. In this one here, just a wire, just a straight line. An open switch shows these as being not connected. Here we have a closed switch. Again, the connection is made so that electrons could flow through that. And then any resistor would be symbolized with this sort of squiggly line. Now, oftentimes what you see is that if the resistance is a bulb, typically there will be a circle around this. And that just lets you know that there's a resistor that is inside the bulb, which would be the filament of the bulb is the resistor. But that's just a little nuance there that you may run across at some point. But here we have a schematic diagram. Here are three resistors connected in series. The switch here is open. Again, here is our battery. And then in the second one, we have a parallel circuit that has been shown with one of the loops being incomplete with this switch being open. If you go back to our 35 notes part 1, these are schematic diagrams of the two circuits that we looked at for series circuits with the 9-volt battery and the bulbs that we were looking at in there. So what symbols are used to represent resistance, wires, and batteries in schematic diagrams? Again, resistance is the zigzag squiggle line. The wires are the straight lines, and the batteries, long line and a short line. Short line, again, the negative, long line, the positive end of the battery. Now, 35.6 is mathy, I would say. It's going to be a little bit hard to go through this. I will try and go through a couple more examples in the math videos I put out next week. But basically, when we combine resistors into a compound circuit, these things can get super jumbled, super cuckoo crazy. We're going to be dealing with some ones that I'm not going to say are cuckoo crazy or anything like that, but they're going to take some time to think about what's actually happening. So there's a couple in the packet that you'll have to do at some point. But the equivalent resistor of resistors connected in series, we talked about in part 1 of chapter 35, is simply add them up. So if you've got a 1, you got a 2, you got a 3, add them up at 6. The equivalent resistance for a pair of equal resistors in parallel is half the value of either resistor. So if you have a 2 and a 2, basically you get 1 ohm resistance for the total resistance of that circuit. Now, I hate that he did it this way because it gives you no idea to the math behind what is happening. We will look at that math a little bit more closely again in the video coming up. It has to deal with something that I don't want to get into with just my voice because it's probably not going to make sense. So anyway, sometimes for a complex circuit, it becomes useful to know what is known as the equivalent resistance for the circuit. And why this is important is because we can start to determine how current, how voltage will set up in this circuit based on, what kind of output the battery or power source is putting out. And so anyway, the equivalent resistance of resistors connected in series, we just add them up. So again, you have a pair of 1 ohm resistors, 1 plus 1 would give us 2. If we have this setup, here we have an 8 and an 8, and those two are in parallel, connected in series with an 8 ohm resistor right here. And so an 8 and an 8 in parallel is going to be half of what they are. So half of 8 is a 4. Well, now you have the 8 from this one here connected to the 4, which is these two 8s here. 8 and 4 would give you 12. And so if we had that passing through there, the equivalent resistance is, twice the path width. So for this one right here, so we have less resistance there. And so equivalent resistance of two 8 ohm resistors in series, 8 plus 8 gives us 16. But if we go parallel, 8 and 8 gives us 4. Again, we go with half of whatever they happen to be. Now, where it gets goofy is if one's 8 and one's 4. If one's 8 and one's 4, you can't just take half. It doesn't work that way. So what we'll do next week is talk about that and make that a little more clear. So for the combination of the 3 8 ohm resistors that we saw back there, 2 resistors in parallel give us an equivalent resistance of 4 ohms. They are in series with the 8 ohm, so the total is 12. If we had a 12-volt battery there connected to it, then the current through the battery would be 1 amp. And effectively through the whole system, we would have 1 amp. In practice, it would actually be a little bit less because a battery always has internal resistance, but it's pretty small. So it's something that we generally would not worry a whole lot about. Now, where we can get a little bit more tricky is if we have a whole lot of resistors in a much more difficult circuit. I don't want to say difficult circuit, one that is much more complex. There we go, a more complex one. And so here we have a 60-volt battery. It is connected to two 10 ohm resistors on this path and a 16 and two 8 ohm resistors on this path. So essentially what we have here is a parallel, a series with these guys, and another series here that's in parallel with this guy. And so what you have to do is, I liken this to, you get a big steak. No one I know of can take a nice big steak and eat the whole thing at once. If you try, you're probably going to choke. You're probably going to die. Okay. If you try and take and figure out what the equivalent resistance of this whole thing is just by looking at it, you're probably going to die. It's going to be hard. Your brain's just going to explode. So what you want to do is you want to take little bite-sized pieces. Everybody can take bite-sized pieces of steak and finish it. So the idea here is, it doesn't really matter where you start as long as you start with little pieces. And so what they did here is they looked at these two 8 ohm resistors in parallel. Two 8 ohm resistors in parallel, we already saw, makes 4 ohms. So boom, there's 4 ohms. Now we have 16 ohms and 4 ohms together. We still have our 10 and our 10 together. These are in series. These are in series. So we add them together. 10 and 10 makes 20. 16 and 4 makes 20. So now we have the equivalent of two 20 ohm resistors in parallel. Two 20 ohm resistors in parallel gives us, again, half of the one of them, which is 10. So the overall resistance, or equivalent resistance, of this whole big old nasty thing is just one 10 ohm resistor. And so at that point, we could take that 10 ohm resistor and say, well, what's the current that's flowing through this particular circuit? Well, the current is going to have to be 60 divided by 10, which is 6 amps of current. Well, that means 6 amps, as it flowed out of this battery, would get here, and it would go, okay, 3 of it has to go here, and 3 of it has to go here. And then it would come back, it would meet, and we're back to 6. And then come back around, goes 3 of it's here, 3 of it's here, come back, meet, and we've got it back there for a total of 6 amps. And so anyway, in the circuit shown below, what is the current in amperes through the pair of 10 ohm resistors? And so the pair of 10 ohm resistors right here, there's going to be 3 amps flowing there. Another way to look at it is given right here. Well, the total resistance in that middle branch is 20 ohms. Well, 60 volts, 20 ohms, guess what? Gives you 3 amps. So you could have found it the way I showed before, realizing that it has to branch here and divide up. Or you could take that 10 and 10, 20, divide it into 60 for 3 that way too. And then through each of the 8 ohm resistors, what is it going to be? Well, 3's going through here, 3's going through here, but when it comes through, it's got a branch. And so it's got a branch half here, half there, and half of 3 is 1.5 amps for each branch. So what is the equivalent resistance of resistors in series? What is it if they are equal and in parallel? Well, if they're equal and in parallel, it's half of whatever 1 is. If they are in series, simply add them up. 1 plus 2 plus 3 is 6. 2 8s gives you a 4 in equal resistors in parallel. All right, so last section has to deal with parallel circuits and overloading. One thing people like to do is they like to get very creative with their plugs. And so unfortunately, they will frequently overload their plugs in a manner that can become unsafe. Well, to prevent you from burning your house down, the state of California has set up some standards that must be met by your electrical panel. It says, well, each circuit in the home gets X amount of current. If that current is exceeded, a circuit breaker or a fuse must stop that current from flowing. If that did not happen, the likelihood of a fire in your home goes up substantially. And they connect it in a way that it's in series, so that when the circuit or circuit breaker or fuse is broken, then what happens is it stops everything on that circuit. Even though there might be several things in parallel, the whole thing is cut off because it's all connected in series. So electrical current is fed into a home essentially by two wires, one in and one out. And we call these lines, gets to your power box, your circuit breakers, which circuit box, which is found usually somewhere on the outside of your home, but not necessarily. About 110 to 120 volts is impressed on those lines by the power utility that you have, PG&E, City of Reading, whatever it happens to be. These lines are low in resistance because they're made out of copper. They're usually pretty big, thick wires running into your electrical panel. And then you have some pretty good lines that run through your house, which are pretty thick copper wires as well. And so the voltage that is applied to appliances and other devices is usually right around 110, 120 as it pulls into those appliances. And then they have resistors on the inside of them, which takes care of the current to run your fridge or run your toaster or whatever it happens to be. Now, as we take more and more devices and we put it onto the same line, okay, give you an example. My wife has a curling iron and a hair dryer plugged in. Well, sometimes she plugs both of them in and is using them at the same time. In that process, she has created a greater current that flows through that line to that particular electrical outlet. And I don't think I've ever seen it click off, but again, more and more you add, the more possibilities there would be to have your circuit breaker or your fuse blow at that point. And so if you get to a certain amount, usually somewhere between 15 and 20 amps, your circuit becomes overloaded if you go over that. If they are over that, it may heat the wires sufficiently to where they begin to melt the insulation. Again, melting insulation could potentially cause the wires to touch, throw sparks. Those sparks light stuff on fire, and all of a sudden your house burns down. And so we don't want that to happen. And so again, if we looked at a toaster, a lamp, and a heater, when we bring the amps, the current in, it branches here, it branches here, it branches here. It may continue on and then come back. But the idea here is I've got 20 amps coming in. I've got 10 amps here, 8 amps here, 2 amps there. Well, if I put something else on here, all of a sudden I may have 25 amps that need to be used on a 20 amp circuit. And if that happens, typically somewhere in your line, again, connected in series, is a circuit breaker, which will say, hey, this is too much. And since it's too much, I have to click off. And if I click off, then your house won't burn down. And you should be thankful for that. But what many times people do is they'll just leave that thing plugged in, and then they'll go buy a bigger fuse or a bigger circuit breaker. Well, your line wasn't meant to have a bigger circuit breaker or a bigger fuse. It was meant to carry that 20 amps, and if you exceed that, it's bad. So anyway, how a fuse works is it's got this real thin piece of metal. Too much current passes through it at one time, and it essentially melts that metal. It's very, very thin, like I said. When that melts, it stops the flow. There would be a cut right here. This whole thing might be melted into a little blob down here at the bottom, but it's not connected anymore. If it's not connected anymore, you have a situation where, because it's connected in series to the rest of your house from this thing, it cuts off that particular section of your house. Maybe it's in your kitchen, maybe it's in your bathroom, wherever it happens to be, but it says, no more. And when there is no more flowing, the big tendency is to go, oh, well, this is a 20 amp. Well, I go buy a 25 amp. Well, you don't want to do that, because you buy that 25 amp one, your lines are only designed for 20. Those lines get hot, start to melt, fires happen. So don't do that. Best thing to do, unplug one of the appliances, move it somewhere else so that they don't keep blowing the circuit. So anyway, look for problems when you're when you have a fuse that blows on a regular basis. Insulation may have been chewed away by a mouse or a rat or whatever it happens to be. It may have just worn. It's old, especially if you live in an old house. This shortens the path of the circuit, which is called a short circuit. Again, fire danger. So large currents can show up, bypasses that normal circuit resistance, which again leads to the possibility for fire. Now, more current homes have these circuit breakers in them. Circuit breakers either have a magnet or a bimetallic strip in them, which click off when too much current passes through. They just know, okay, it's X amount of current, click off, and I can't allow it to happen anymore. So you have to go out. The nice thing here is you don't have to go and buy a brand new fuse every time. You just go to your circuit box, click it off, click it back on, and assuming that you have taken care of the problem, too many things plugged into the same plug, whatever it happens to be, it'll work again. But utility companies use circuit breakers to protect all their lines so that, if something happens, a lightning strike, stuff like that, it protects their generators and the important stuff that's back at the plant that sends the electricity out. So circuit breakers are, again, in more modern buildings. They typically require you, if you fix your house, if you still have fuses, you have to fix your electrical panel to include circuit breakers anymore. So how can you prevent overloading in circuits? Essentially, you don't plug too many things in. Make sure your wires are good. If there is something that continues to happen over and over again, you might want to consult an electrician. All right, well, that's chapter 35. Again, look for some of those math videos coming out. We'll go over some of that parallel equivalent resistance type stuff and some of the V equals IR from chapter 35 or 34 so that you're all good to go on that. Again, if you have any questions, twyrick@auhsd.net. Have a good weekend.